so let's talk about the acid-base properties of salts. So you would have learned in General Chemistry 1 about the neutralization reaction. And what you may have been told is that in the neutralization reaction, we react an acid with a base to form a salt and water. The acid would be acidic, the base would be basic, and the products will be neutral. Well, that is not entirely true. It's true in some cases, but not true in all cases because the salt itself can display acidic or basic properties. And it actually depends on the acid and base that comes together to form the salt. So we're going to look at the different types of salts in terms of their acid-base properties. And the first type we're going to look at are the neutral ones. These are salts containing alkali metal or alkaline earth metal ions, excepting beryllium 2 plus, and the conjugate base of a strong acid, for example, chloride, bromide, and nitrate. So therefore, these salts, when dissolved in water, does not have any effect on the pH of water. So a good example of this is sodium chloride. If you add sodium chloride to water, you get sodium and chloride ions, and these ions do not interact with water to form anything acidic or basic, so therefore the solution remains neutral. In the case of basic solutions, that is different because basic solutions, firstly, let me just say that they're derived from a strong base and a weak acid. So if the salt is derived from a strong base and weak acid, then that solution is going to be basic. So an example of this would be sodium acetate. And the formula for this is wrong. This hydrogen should not be here. In any case, when this is added to water, it forms Na plus and CH3OO minus, right? Now, the sodium ion, just like the sodium ion in this case, will not have any effect on the pH of the aqueous solution. However, the acetate will act as a base when it reacts with water to form acetic acid and the OH minus. And it is because of this OH minus that is produced, the solution, the resulting solution is going to be basic, right? So that explains why basic solutions are formed from salts, which are themselves formed from a strong base and a weak acid. Then we get to the category of acid solutions, and these are acid salts that are derived from a strong acid and a weak base reacting with each other. So a good example of this would be ammonium chloride. Ammonium chloride is such a salt that when dissolved in water, it forms the ammonium ion and the chloride ion. The chloride ion is a very, very weak base and therefore does not interact with water to change the pH. However, the ammonium ion will dissociate to form ammonia and H+, and it is this H+, which makes the solution acidic. All right? Then there's a third category. Oh, before I get to the fourth category, we also have salts which have a small highly charged metal cation, such as these: aluminum, chromium-3, and beryllium. And it's combined with a conjugate base of a strong acid. In this particular case, these acids or these salts will be acidic as well. And there's a reason for that. Using the aluminum example, what happens is that the aluminum will be immediately surrounded by water molecules, and then you'll have the spontaneous emission of a hydrogen ion, which results in the solution being acidic. Now, to explain this further, we have this diagram right here. This is the actual structure of the aluminum ion surrounded by the water molecules, right? And then what will happen is that one water molecule from the environment will come close and donate a pair of electrons to one of the hydrogens here, right? So therefore, as a result, you're going to end up with the hydronium ion being formed. I'm sorry about that. The hydronium ion being formed, and you have the rest of the structure here remaining. And that explains basically the acidity of salt solutions containing small, highly charged cations such as aluminum. Okay, so this is basically a situation. Let me see here what we have. Oh, so let's talk about a situation where you have both the cation and the anion interacting with the water. So the question is, which one will determine the resulting pH of the solution? Well, if the Kb for the anion is greater than the Ka for the cation, then the solution will be basic, right? In other words, if the anion is a stronger base compared to the acidity of the cation, then the solution is basic. The reverse is true if Kb for the anion is less in value compared to the Ka for the cation, In that case, the solution will be acidic. All right. So that's basically what happens in the case of a solution of, let's say, sodium, or I should say ammonium acetate, right? What you'd have to do is look for the Ka value for the ammonium ion, look for the Kb value for the acetate ion, and compare the two. The one that is greater in value is what will determine whether or not the solution is acidic or basic. And below here is a table which basically summarizes all that I have just discussed. Some examples of different salts are given here, and the resulting pH of the solution that will be the result when these salts are dissolved in water. All right. One more thing I should have mentioned here: if Kb is equal to Ka approximately, then the solution is neutral. All right. So that makes sense. If the strength of the conjugate base is equal to the strength of the conjugate acid, then the solution will be neutral. All right. So this here is basically a periodic table with some oxides of these elements formulas being shown, and it shows you basically that some of these oxides, mainly the non-metallic ones, are acidic. In other words, when added to water, it forms an acid, such as carbon dioxide and dinitrogen pentoxide. These are both acidic gases, which would form acids when dissolved in water, right? And that tends to be the case for non-metallic oxides, which would be to the right of the periodic table. The metallic ones tend to be more basic, such as the lithium, sodium, and so on, right? And then you have some oxides that are said to be amphoteric. Amphoteric oxides are basically oxides which displays both acidic and basic properties, such as aluminum oxide, selenium 4 oxide, and so on, lead 4 oxide, etc. All right. So let's go back to the definitions that we talked about for acids and bases. So remember, we said, and we're going to stick to acids in this case, and we can, of course, see the correlation with bases. So remember, we said that according to Arrhenius, an acid is a substance which, when added to water, produces H plus ions. A Bronsted acid is basically a proton donor. But there's yet another definition, which is known as the Lewis definition. The Lewis definition is dependent or based on whether or not a substance can accept or donate electron pairs. So according to this definition, a Lewis acid is a substance that can accept pairs of electrons, while a Lewis base is a substance that can donate a pair of electrons, right? So if we go back to this example of H plus reacting with OH minus, right? What will happen when these two combine is that a pair of electrons will be donated from the OH to the H plus, and more specifically from the oxygen to the H plus. And the result will be the formation of the water molecule. So therefore, according to the Lewis definition, the H plus would be the acid because it accepts an electron pair, while the base would be the hydroxide because it donates an electron pair from, to the acid. All right? So that's basically the Lewis definition of an acid and a base. Here's another example. H plus added to ammonia. Again, H plus would be the acid in this case because an electron pair is donated from the nitrogen to the hydrogen. So H plus would be the acid, the ammonia would be the base, and of course the product would be the ammonium ion. All right? So that's a third definition that you have to keep in mind. Now, what you need to recognize when it comes to these definitions is that there's no clear conflict between them. However, what will happen, you'll notice, is that, for example, the Arrhenius definition is very limited because it's based on what the substance does in water. The Bronsted definition is more embracing a lot more substances because it does not require the water involvement, right? And when it comes to the Lewis definition, that broadens the definition of acids and bases because in that definition, water is not involved and it does not necessarily, or water is not necessarily involved and it does not necessarily involve the presence of a proton either, all right? In fact, let me see here. Here's one example of a Lewis acid-base reaction where there's no water and there's no hydrogen ions being transferred. So this is boron trifluoride reacting with ammonia, right? And in this particular case, this pair of electrons will be donated to the boron, right? So the resulting product would be this, right? And you'll notice that because this is accepting electrons, the boron trifluoride will be the acid, and the ammonia will be the base, and you end up with a product. So in this case, there's no hydrogen ions being transferred. So according to the Bronsted definition, this would not be an acid-base reaction. There's no hydrogen ion being produced, or OH minus ions. So therefore, this would not be, according to Arrhenius, an acid-base reaction. But according to the Lewis definition, this would be an acid-base reaction because it involves electron transfer, right? So there are no protons donated or accepted, and therefore we can say that this is a Lewis acid-base reaction, but it won't be a Bronsted definition. By Bronsted definition, an acid-base reaction. Okay, one last thing I want to talk about here in this chapter, and this is basically talking about the applications of acid-base reactions when it comes to certain antacids formulations, right? So these are just some examples of commercially available antacids, such as Alka-Seltzer, Bufferin, milk of magnesia, Rolaids, and so on. And if you look at the active ingredients that make up these preparations, you'll see that they're all basic, right? They all react with acids, right? Because that's your function, to relieve heartburn. Heartburn is a bit of a misnomer because what is actually happening when somebody is suffering from heartburn is basically there's an excess of acid that is produced by the stomach, right? The acid normally produces hydrochloric acid, but sometimes it produces too much, right? And therefore, to relieve the symptoms, these formulations have been put together which contain bases. So when you consume these formulations, there's an acid-base reaction that occurs so as to reduce the acidity. So for example, bicarbonate of soda, which is sodium bicarbonate, will react with hydrochloric acid according to this equation, all right? Milk of magnesia will react with hydrochloric acid to form magnesium chloride and water. So these are all examples of reactions which are acid-base reactions based on the formulations that are used, which contains these basic products so as to reduce the acidity in your stomach, relieving heartburns. Okay, so this is basically the end of this chapter. So the next video we'll be dealing with some other equilibrium situation and aqueous solutions. All right, until next time.